we define a graph trapezoid for 2 points on the graph of some function as follows. Okay, we form the trapezoid first by 2 projection lines, one from each point. By projection line, I mean a point parallel to the horizontal axis. So we have our, perpendicular to the horizontal axis. So I draw a projection line from this point to the horizontal axis and from this point to the horizontal axis. Then we have the approximating segment, which I also call, quote, slope segment. And that's simply the line segment that joins the 2 lines. Straight line segment joining the 2 lines. And now we see that with the horizontal axis and the projection lines and the slope segment, we have a trapezoid. Trapezoid being characterized by the fact that we have exactly 2 parallel sides. It's a quadrilateral with exactly 2 parallel sides. We label this trapezoid. First thing we label will generally be the projection lines, which are labeled with their lengths. Now those lengths look like altitudes because they run perpendicular to this thing that we want to tend to think of as the base. Now in fact, from here to here is actually the altitude of the trapezoid, and we would regard these as 2 different bases. That would be the traditional way to do it. But when we're doing this with graphs, we call these graph altitudes. They're not really altitudes. There's only one altitude of a trapezoid, but it's going to be easier for us to think of this if we think of what we do with these trapezoids, if we call these both altitudes. So this altitude we could label with a number that would represent the altitude of this side, and this with a number that we could take to represent the altitude of this projection line. Okay. Then we label the interval of the axis with its width. Okay, so from here to here is the width, so we put the width down here, and we understand that the number we put here is going to stand for the width of the trapezoid. Then we label the approximating segment, that is the segment joining our 2 points, with the slope. Okay, now there are cases where we would also want to label this with its length, which we would calculate using the Pythagorean theorem. But I'm going to use the convention that we label the slope here. We put a number in a box, and we understand that the number in the box above this segment represents its slope. And then finally, if we have this information about altitude 1, altitude 2, and the width, we can easily enough calculate the area of the trapezoid, and we would label that inside the trapezoid, and we would call that the area. So that is going to be the standard labeling of a trapezoid. Now, we'll give an example, and we'll calculate these quantities and just illustrate how we would calculate a slope and an area. Okay, here I've got a copy of our trapezoid. It's not an exact copy, but represents a trapezoid with altitudes and a width. Now, how would we get the altitudes and a width of the trapezoid? Well, that depends on the situation, but if we have the 2 graph points, if we know the coordinates of the 2 graph points, then we can easily determine the width and the 2 graph altitudes, and that should be straightforward. We'll do that in examples, but I'm assuming that if you know the x and y coordinates, say, of this point and this point, you can easily find the 2 graph altitudes, which are the y coordinates, and the width, which is the change in the x coordinate from here to here. With that labeling, what can we do? Well, can we calculate the slope of the trapezoid, and can we calculate its area? Now, one thing I don't want anybody to do here, at least when actually working with one of these trapezoids, you'd be fine to do it now as a curiosity and a confirmation that what we're about to do to find the area works. But I don't want you pulling out the formula for the area of a trapezoid. I think that formula is completely unnecessary if you have even the most rudimentary understanding of geometry, and I'll explain what I might mean by that. Okay, so, well, let's calculate the slope. Now, how do we calculate the slope of this trapezoid? Hopefully you've thought about that before you watch me do it, but the slope between 2 points is the rise between those points divided by the run between those points. So we can calculate, or we can sketch or complete a triangle up here where this line is perpendicular to the altitudes, meaning it's parallel to the segment of the x-axis, or the horizontal axis, and is therefore equal in length to that segment. So don't want to use up too much space here, but I'm saying the run is clearly 5 if we go from this point to this point. And what's the rise? Well, it should be very clear to you that the rise is from 18 to 24. So that the rise is, I could write 24 minus 18 equals 6, but it should be completely obvious to you that the rise from here to here is the change in the y-coordinate, and that is 6. Now, I've indicated that by an arrow. I could indicate this run by an arrow. And then from that I can determine the slope. The slope is rise divided by run, which is 6 divided by 5, which is 1.2. So that now, in keeping with the conventions, I put the slope in a box above the approximating segment or the slope segment. So that slope is 1.2. Now, how do we calculate the area of a trapezoid? You might want to think of that, and I prefer that you do it geometrically and don't go back to a formula. Geometrically, and I'll pose the question, how could we take a trapezoid of this nature, assuming we have right angles here and here, how do we take that trapezoid and construct an equivalent rectangle, that is, a rectangle with the same area? Now that's worth some thought. You might think about stopping and trying to do that. There are actually 2 ways to do that that I know of. I haven't proven that there isn't a third way, but if you could, that would be great. Okay, hopefully you've thought about that. Hopefully you've seen at least one way to represent or to construct a rectangle equivalent to this trapezoid. The way I'm going to do it is I'm going to say, well, the midpoint of the segment, the approximating segment, is right here. If I cut off the right triangle formed, if I move horizontally from here to here and flip it over and put it here, I now have a rectangle of equivalent area. So I can emphasize that rectangle with the closest thing I have to red chalk. And there's the rectangle. The rectangle has an area that's equal to that of the trapezoid. And I haven't done the entire geometric argument, but if this is the midpoint, this side is equal to this side. And this being horizontal, we have a right angle here and a right angle here. And then this side also is going to be equal to this side, etc. So we're going to have 2 similar triangles, 2 congruent triangles here. So the triangles are congruent, And actually, we can't necessarily conclude this side equal to this side, but this angle is equal to this angle, and we have right angles, meaning all three angles are the same. This side's the same as this side if this is the midpoint. Therefore, the triangles are congruent, and that's an argument you should be able to reconstruct, and arguments of similar nature throughout the course. So now we see the original trapezoid in white and a rectangle in red whose area is equal to that of the trapezoid. Now, if the altitudes of the original trapezoid were altitude 1 and altitude 2, then what are the dimensions of the rectangle? Okay, most specifically, we do know the width of the trapezoid, and that's going to be the same as the width of the rectangle. What's the altitude of this rectangle? Now you think of length and width. I'm saying length and altitude, but just because of the way the thing is oriented on the page here, or on the board, you can think this is width and this is length if you like, but I'm going to talk about altitude. So it is an altitude because it's perpendicular to a base. So what is the expression for the altitude of, or this dimension, whatever you want to call it, of the rectangle? Okay, so we see that we've constructed a rectangle whose area is equal to that of the trapezoid. If we know the two altitudes, the graph altitudes of the trapezoid, how can we find the dimension of the rectangle? Well, should be obvious. Now there's a geometric proof, and you should hopefully have a background in geometry that allows you to rigorously prove this. It would be good practice for some of the things we'll see later in the course, the geometrical aspects of things that we want to discuss, that we can just average these two altitudes in the sense of adding them and dividing by 2. That's going to give us an altitude that's exactly halfway between this one and this one. And this altitude occurring at the midpoint along a straight line connecting the 2 points, 2 graph points, is going to be equal to that. So we're going to say this is the average altitude, and we can depict that average altitude by a dotted line here if we wish. So now, what area follows from these observations? What is the area of this rectangle in terms of the width and the two altitudes? Well, the area of a rectangle is the product of its two dimensions, the width and the length, or the width and the altitude, whatever you want to call those two dimensions, the lengths of the two lines, two perpendicular lines that make up sides of the rectangle. So now, if we come up here, how do we calculate the altitude of this particular trapezoid? Well, the calculation of the area is now really straightforward, and you might well have seen this a long time ago, but the average altitude for this triangle, or trapezoid, is 21. And if you reached for a calculator to calculate that, there's something seriously amiss. First place, we know that the average of these numbers is halfway between them, and if you've got a calculator in your fingers, counting your fingers, that's better than using a calculator, because at least you're engaging your brain in the calculation. 18, 19, 20, 21, 22, 23, 24, 6, and half of that is 3. 18 and 3 is 21. 21 is as close to 18 as it is to 24. There's no justification for reaching for a calculator to do that calculation. And people will. People won't reach for a calculator to add 2 and 2. Very, very bad. Okay, if you're multiplying 746 by 38 and need 3 or more significant figures, then by all means reach for your calculator. That'd be ridiculous. Long division of most numbers, yeah, that's fine. But don't do it for simple calculations. Okay, anyhow. So the area is what? It's average altitude times width. We already know the width to be 5. We calculated the average altitude. So the area is 21 times 5, which is 105. The last thing we do is we complete the labeling. We need to have the area probably somewhere around the center of the trapezoid, depending on what else has been labeled. And we put a circle around that. And we understand now, in looking at this trapezoid, that it has altitudes 18 and 24, width 5, slope 1.2, and area 105. There's the basis for all of calculus, as we're going to see.